All right, 11.1. So we're still talking about hypothesis testing. As I've mentioned, this entire unit is about hypothesis testing. Um, the stuff we did in chapter 10 was all hypothesis testing regarding a single parameter. Now we're going to be talking about hypothesis testing that involves two different parameters. So in 11.1 and 12.3, we're going to talk about how to run hypothesis tests on two proportions. And it used to be in your textbook that they did both of those topics in the same chapter. 11.1 and 12.3 were all condensed into just one section. But they've split it into two sections, and they put the second half of the section in chapter 12. I don't agree with that change, needless to say. So we're going to cover 11.1 and 12.3 back to back, the way that it initially was in your textbook in the previous edition before the one that we're using right now. Anyway, one of the things that we need to be able to do when we are running hypothesis tests on two parameters is we need to know if the two samples that we're looking at were obtained independently or dependently of each other. So let's talk about what that means. It's the same concept of independence that we've talked about in the past, but maybe from a slightly different perspective, because we're talking about whether or not samples were independent or dependent. So a sampling method is independent if the individuals selected for one sample do not dictate which individuals are to be in the second sample. The sampling method is dependent when the individuals selected to be in one sample are used to determine the individuals in the second sample. Dependent samples, for that reason, are sometimes referred to as matched pairs samples. Okay? So to give you an example of this, just kind of offhand, a dependent sample would be something like this. If we were interested in comparing the way that husbands and wives compare on some certain issue, then we might go out and collect a sample of husbands. And once we've collected that sample of husbands, then the second sample of wives is automatically determined based on who we chose for the husbands to be in the sample. And then we get matched pairs, obviously, because so each husband is a matched pair with his wife, right? So that's why they're called matched pairs samples. So that would be a sample of a dependent sample. If the samples are dependent, it's usually going to be something pretty clear like that. If there aren't any kind of link, if there isn't any kind of link between the samples, right, then if there are no matched pairs, then the samples are independent. So let's look at a couple examples. This one says, among competing acne medications, does one perform better than the other? To answer this question, researchers applied medication A to one part of the subject space and medication B to a different part of the subject space to determine the proportion of subjects sorry, I lost my place. I looked away for a second and lost my place. To determine the proportion of subjects whose acne cleared up. The part of the face that received medication A was randomly determined. So the sampling method used here. Well, let's think about this. Really, it looks like the researchers only collected one sample, right? They just collected a bunch of subjects, and they applied a medication to half of that subject space, and then they applied a different medication to the other half of the subject space. So even though it's one sample, we could consider it two separate samples. We could consider it one sample of people to whom medication A was applied, and we can consider it a second sample of people to whom medication B was applied. And if we view it through that lens, then the way that we chose the sample for medication A automatically determined the way that we chose the sample for medication B, right? Because because it's the same exact individuals, right? The same individual got medication A applied to one part of their face and then medication B applied to a second part of their face. So the sampling method used here would be dependent sampling. Dependent sampling, because once a subject is chosen for medication A, a subject is chosen for medication B. In this case, it's the same exact subject for both medications, okay? Here's another example. So it says, do individuals who make fast food purchases with a credit card tend to spend more than those who pay cash? To answer this question, a marketing manager randomly selects 30 credit card receipts and 30 cash receipts to determine if the credit card receipts have a significantly higher dollar amount on average. Let's just say have. Okay. Well, so the sampling method used here, well, let's think. So they randomly selected 30 credit card receipts, and then they randomly selected 30 cash receipts. It doesn't say that they followed around the same person and observed them until they paid with cash, and then observed them until they paid with credit, and then collected their cash receipts and their credit receipts and compared the two. It doesn't say that, right? It just says that they randomly selected 30 cash receipts, and then they randomly selected 30 completely different credit card receipts. So there are no matched pairs here. Those two samples are not related in any way. So this sampling is independent. Okay, so independent versus dependent samples. Now you may wonder, well, why does it matter? And the answer is because if you have dependent samples, you can do the analysis that you can do is a little bit stronger than if you have independent samples. Now that said, you can't always get dependent samples. So if you can't get dependent samples, then we can still run some pretty good tests on independent samples. And that's what the topic is today. So we're going to talk about inference on two proportions, so hypothesis testing on two proportions when the samples are independent, okay? So here's another set of examples. I'll let you pause the video and see if you can figure out if the sampling method used is independent or dependent on these two examples. So go ahead and give the video a pause and see if you can answer the questions. Okay, I'm gonna go ahead and give you my answers now. So this first one says, so Joliet Junior College decided to implement a course redesign of its developmental math program. Students either enrolled in a traditional lecture format or a lab-based format. There were 1,200 students in the enrolled in the traditional format, and 300 in the lab-based format. At the end of the semester, the researchers evaluated the performance of each group. Okay. Well, first of all, right off the bat, the sample sizes are not the same. So they can't be matched pairs, right? How can you match up 300 people with 1,200 people in a one-to-one fashion? You can't, right? So they're not matched pairs. So right off the bat, you know that this is not dependent sampling. This must be independent sampling. But even more fundamentally than that, if you just read through the scenario, it's not like if a student enrolled in a traditional format that the college automatically chose another student and just automatically enrolled them in the lab-based format. That's not what happened. Each student independently chose whether they wanted to be in the traditional format or the lab-based format. So this is independent sampling for sure. But yeah, a pretty dead giveaway that you have independent sampling is if your sample sizes don't match, okay? That doesn't mean that if your sample sizes do match, that automatically you know it's dependent sampling, because that's not necessarily true. But at least you can say if the sample sizes are different, then the sampling must be independent. Okay, next question. Do women tend to select a spouse who has a higher IQ than their own? To answer this question, researchers randomly selected 20 women and their husbands. They measured the IQ of each husband-wife team to decide if there is a significant difference in IQ. Okay, so I kind of gave this one away with the example that I gave earlier, but these would be dependent samples for sure, right? You collect a sample of wives and then you go out and select a sample of husbands. But once you've selected the sample of wives, the sample of husbands was automatically determined because you had to choose the wife's husband, right, to be in the second sample. So these are dependent, they're matched pairs, right? Dependent samples for sure. Okay, so with that in mind, now here's some notation that we're gonna use. It may look like a long, scary list, but it's not really all that scary. You already know what P and N and X stand for. Now we're just using subscripts 1 and 2 to differentiate between the first and second groups in the study. So P1 is the population proportion of the first group, P2 is the population proportion of the second group. N1 is the sample size of the first group, N2 is the sample size of the second group, and so forth. P1 hat, so that's the sample proportion of the first group. That would be X1 over N1, right? And P2 hat would be X2 over N2. Now, if you don't have a subscript, if you just have P or P hat, those are the common proportions. So P is the common population proportion, P hat is the common sample proportion. So it's like if you put both of the samples together and pooled their observations, then P hat is that sample proportion, right? So P hat would be, in this case, X1 plus X2, right? All of the successes in both of the trials, or in both of the studies, divided by N1 plus N2, right? The total number of individuals in those studies. And this is sometimes called the pooled estimate of P. I just mentioned that in case you have a homework problem that asks you to calculate the pooled estimate of P. Honestly, I'm never going to ask you to do that on a test or a quiz, but anyway. With all that notation in hand, this is how hypothesis testing looks when you're testing two proportions. So as usual, you're going to state the null and alternative hypotheses. Okay, you can have left-tailed, right-tailed, or two-tailed tests. But what you'll notice now is that instead of the null hypothesis being P equals some value, your null hypothesis is always that P1 equals P2. And you're never going to have numbers in place of that. You're literally just going to write down P1 equals P2 for your null hypothesis every single time. And then you have to decide if it's two-tailed, left-tailed, or right-tailed. Once you've written down your hypotheses, then you can calculate the test statistic. This is pretty nasty. I'm not going to do any of these by hand, okay? But you would compute your test statistic at this point. And if you squinted it just right, then you'll kind of notice that this is a z-score, right? It's a z-score for the difference between P1 and P2. Okay, once you have your test statistic, then you use it to compute the p-value. The p-value is the probability that you observe your test statistic or something more extreme than that. Right, so for a two-tailed test, this is the p-value you want. For a left-tailed test, this is the p-value you want. For a right-tailed test, this is the p-value you want. Of course, StatCrunch is going to do these two steps for us simultaneously, right? So you don't have to worry too much about that. But what I do want you to understand is, again, what does the p-value represent? The p-value is the probability that we obtain the sample statistic that we obtained if we assume the null hypothesis to be true. So if that probability, if that p-value is really small, then it casts doubt on our assumption. And so in that case, we would reject it, right? So if the p-value is small, and in particular, if it's less than alpha, our level of significance, then we reject the null hypothesis. And then last but not least, of course, we write a conclusion, which is a statement about what your decision means for the alternative. With any hypothesis testing, there are going to be conditions that we have to check in order to run the test. I don't make a huge deal out of this. I'm not going to emphasize this a ton, but just for your information, like in the real world, these are conditions that you'd have to check in order to run this test. Okay. If you want a little more detail about where this test statistic comes from, like I said, it's basically a z-score, right? But if you want to see a full derivation of the test statistic, look at pages 526 and 527 in your textbook. So I'm not going to get into all of it in a ton of detail. Here's how you run the test in StatCrunch. You're going to go to Stat, Proportion Stats, of course, because we're running a hypothesis test on proportions. But what's different now than what we did before is that you're going to go to toSample because you have two samples, right? When you get there, StatCrunch is going to state the null and alternative hypotheses a little differently than we did. So instead of saying P1 equals P2 for the null hypothesis, they're going to say P1 minus P2 equals 0. But those are equivalent statements, right? If P1 equals P2, then you can subtract P2 from both sides of the equation and get P1 minus P2 equals 0. If they're the same number and you subtract them, you get 0, in other words, right? And same thing with all of the alternatives, right? If you have a two-tailed test, it's still going to be two-tailed in StatCrunch. It's just going to be stated a little different. If you have a left-tailed test, it's still going to be left-tailed in StatCrunch, and so forth. So let's go back up to the top of this page and work out this example. It says, an economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. He obtains a sample of 800 urban households and finds that 338 of them have internet access. He obtains a random sample of 750 rural households and finds that 292 of them have internet access. Test the economist's claim at the 0.05 level of significance. Test his claim. Well, what's his claim? Well, he believes that the percentage of urban households with internet access is greater than the percentage of rural households. So let's call urban households group 1, since they were the first ones mentioned, and then rural households would be group 2. The null hypothesis is that the proportions are the same, right? The proportion of individuals in urban households who have internet access is the same as that in rural households. The alternative hypothesis is what we're trying to test. We're trying to test his claim. His claim is that the percentage in urban households is going to be greater than the percentage in rural households. So he thinks P1 is going to be greater than P2. Well, what evidence does he have to make this claim? Well, for urban households, he sampled at 800 households and 338 had internet access. So P1 hat would be 338 out of 800. And that's about, so that's exactly equal to 42.25%. Oh, maybe I'll give it as a decimal, 0.4225. Okay, so there's P1 hat, P2 hat, the second sample. For the rural households, he sampled 750 households and found that 292 of them had internet access. That's 292 out of 750. Well, let's see. That's about 0.3893. Okay, so about 42% here and about 39% there. So P2 is definitely smaller than P1, or in other words, P1 is definitely greater than P2. P1 hat is greater than P2 hat, I guess I should say. But is that sample evidence enough for us to safely conclude that the population proportion of urban households would be greater than the population proportion of rural households? Well, we don't know. We have to run the test, right, to see. So we're going to go to Stat, Proportion Stats, toSample. With summary. When we go there, we will be prompted to enter the number of successes for each group, which we just wrote down, and the number of trials for each group, which we just wrote down. So that's group 1. For group 2, it was 292 out of 750. Okay, let's go to StatCrunch and see what we get. So stat, proportion stats, 2 sample with summary. So I have 338 out of 800, and I have 750 out of, oh, I'm sorry, 292 out of 750. I want to test to see if P1 equals P2 against P1 greater than P2. And there we go. Right, there's our p-value, 0.092. Okay. Well, is that good enough? It would be good enough if our level of significance were 0.10. But our level of significance is 0.05, and that's not less than 0.05. So no, it's not good enough, right? So our decision is, since 0.092 is not less than 0.05, we do not reject. The null hypothesis. So, at the 0.05 level of significance, there is not sufficient evidence to conclude there is not sufficient evidence to conclude that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. So you can just copy and paste, right? I'm going to abbreviate a little bit and say the percentage of urban households with internet access is greater than that of rural households. And that's that, right? So at the 0.05 level of significance, there's not sufficient evidence to conclude that the percentage of urban households with internet access is greater than that of rural households. Okay, so, and again, the p-value, right? The p-value. So what this means is that if we assume that the percentages are the same, then the probability that we would get sample statistics that differed by this much is about 9.2%. So there's a 9.2% chance that we would observe these sample statistics if the true proportions were equal to one another. And that's on the low side for sure, but it's not low enough for us to be doubtful about our null hypothesis in this case, right? The threshold that we set for ourselves before we started the problem was 0.05, and this didn't quite beat that. So we don't reject the null, okay? Anyway, so that's that one, that's example 2. Let's look at a couple more examples. I'll let you pause the video and see if you can do this one. It says, Johns Hopkins researchers conducted a study of pregnant IBM employees. Among the 60 employees who worked with glycol ethers, 20 had miscarriages. That's a lot. But among 750 who were not exposed to glycol ethers, 120 had miscarriages. That's still a lot. Using StatCrunch at the 0.01 level of significance, test the claim that the miscarriage rate is greater for women exposed to glycol ethers. Man, If this is true, this is bad news for IBM, right? It means they have a lawsuit on their hands, I would guess. But anyway, go ahead and pause the video, see if you can work this one out. Okay, here's my solution. So right away, I know the null hypothesis is going to be that P1 equals P2, although I should decide before I go any further which group is going to be group 1 and which group is going to be group 2. It doesn't matter as long as you stay consistent through the problem. So I'm going to say the group that was exposed to glycol ethers, I'm going to call that group 1. And then the group that was not exposed, I'm going to call that group 2. We want to test the claim that the miscarriage rate is greater for women exposed to glycol ethers. So we want to test to see if this is greater than that. All right, so P1 greater than P2. That's what we want to test. Well, what sample evidence do we have? For the women exposed to glycol ethers, 20 had miscarriages. It was 20 out of 60, which is about 0.333. For women not exposed, 120 had miscarriages out of 750. Let's see about how much that is. Well, that's exactly 16%. That's quite a bit less than that. This is less than half the percentage of than that. So, or I don't know what I just said. This is less than half of that, is what I'm trying to say. So, so I would be very surprised if we don't end up rejecting the null hypothesis. I would say we're almost certainly going to be rejecting the null hypothesis here. But just to be sure, let's go ahead and run the test. I mean, our threshold level is pretty small, so maybe we won't reject, but only because alpha is so small here. But let's see. We're going to go to stat, proportion stats, to sample with summary. By the way, I want you to write this stuff down on your tests and quizzes. Okay, if you get the wrong answer, but you wrote all this stuff down, I can still give you 4 out of 5 points. You know what I mean? And it happens, right? It happens that you just accidentally write in the wrong number into StatCrunch and then you get the wrong result. And if I don't see any supporting work, then I mean 0 points for that. You know what I mean? So write this stuff down. So we had 20 out of 60 for group 1. And then we had 120 out of 750 for group 2. So make sure you write all of this stuff down for me on tests and quizzes. But let's see what we get now for the p-value. So let's go to StatCrunch. So it's stat, proportion stats, to sample with summary. We have 20 out of 60 for group 1, 120 out of 750 for group 2. We want to run a right-tailed test. Okay, so there's our p-value, 0.0003. So just as I suspected, right? That's a really small p-value. That means that there's a 0.03% chance that we would have observed these things if in fact the proportions were the same. That's really pretty unlikely. And so it means that our assumption is probably not true, so we reject it, right? So our p-value is 0.0003. Our decision is reject. We'll say since 0.0003 is less than 0.01, we reject the null hypothesis. So in conclusion, then we'd say at the 0.01 level of significance, the evidence suggests that, well, the evidence suggests that the miscarriage rate is greater for women exposed to glycol ethers. Miscarriage rate okay. And that's that one. So again, bad news for Johns Hopkins, right? Okay, so that's that. One more, just for good measure. It says, in clinical trials of Nasonex, 3,774 adult and adolescent allergy patients were randomly divided into two groups. The patients in group 1 received 200, what is that, micrograms, 200 micrograms of Nasonex, while the patients in group 2 received a placebo. So a sugar pill, right? You remember about placebos, okay? Of the 2013 patients in the experimental group, 547 reported headaches as a side effect. Of the 1,671 patients in the control group, 368 reported headaches as a side effect. Is there evidence to conclude that the proportion of Nasonex users that experience headaches as a side effect is greater than the proportion in the control group? So go ahead, pause the video, see if you can work it out on your own. Okay, here's my solution. Okay, null hypothesis. This time I don't need to label stuff. They already labeled them for us, group 1 and group 2. So what is it that we want to know in the alternative? We want to know if the proportion of experienced headaches as a side effect is greater than the control group. So we want to know if the experimental group is greater than the control. So group 1 greater than group 2. P1 greater than P2. Well, what evidence do we have? Well, in the experimental group, 547 out of 213 said that they experienced headaches. Okay, so that's about 0.272. In the control group, 368 out of 1671 said they experienced headaches. Now these people didn't even receive a medication, right? They just received a placebo. So these people just tricked themselves into thinking that they were getting a headache as a side. Maybe they really did experience a headache, right? But they were going to get a headache anyway that day. It had nothing to do with the placebo they took. 1671. So that's about 0.220. So yeah, this is about 5 percentage points less than that. Or in other words, this is about 5 percentage points more than that. So that is a pretty big difference. Is it a big enough difference to reject the null hypothesis? Well, we'll see. So we're going to go to stat, proportion stats, to sample, with summary. Okay, in group 1 we had 547 out of 2013. In group 2 we had 368 out of 1671. Let's see what we get for our p-value. Stat, proportion stats, 2 sample, with summary. So it's 547 out of 2013, 368 out of 1671, and then we want a right-tailed test. Okay, another really small p-value, so we're going to be rejecting the null hypothesis again. So our p-value is 0.0002. Since 0.0002 is less than 0.05, we reject. Okay? So at the 0.05 level of significance, the evidence suggests that Nasonex users experience headache, are more likely to experience headache as a side effect. We'll say that. Nasonex users are more likely to experience headaches. That's bad news for Nasonex. That means that they have to list headache as a side effect of Nasonex. You know, in the commercial when they start to list off all the negative side effects, right? So they have to list headache now as one of them, right? Anyway, so that's that. Here's the homework. I say for 9 and 11, don't use StatCrunch. Forget that. Go ahead and use StatCrunch on all of it. But still skip part C, I suppose. Oh, yes, skip part C. I think on some of these things, there's more than one way to run a hypothesis test, okay? But they're equivalent, logically speaking, and so you end up with the same decision either way. But I'm not going to show you the other way. It's kind of an old-fashioned way to do it. Relies a lot on charts and stuff like that. Since we have StatCrunch, the easier approach is to just take the p-value approach. But I'm telling you this because I think in part C on these two problems, they're having you do it using kind of the classical approach, and it's just not important in this day and age to learn that. So you can skip part C on those problems. Okay, so that does it.